going also, so if you haven't responded to that, go ahead and respond to that. All right, so today we are going to talk tidy data, okay? And I'm lifting content directly off of stuff produced by Garrett Grolman and Hadley Wickham. They're both employees at our studio. Hadley Wickham, he's like the master of R, okay? He's written so much, and Garrett Grolman's a excellent teacher for R stuff, okay? And so anyway, a lot of this is coming from this book, R for Data Science. Highly recommend this book, and it's free for you guys to read, okay? You guys all know about Safari Books Online? Do you guys all know about this resource that you guys have? No? You guys are shaking your head. Okay. That is what happened last class too. Okay, so you guys are paying money to UCLA, right? And your money goes to all sorts of different stuff, right? Some of it comes to me as pays my salary, okay? But a lot of it goes to different things around campus, right? Some of it goes to Gene Block, and but some of it goes to the library system, okay? And we have an excellent library system, and I don't know how often you go to the physical library. I don't go to the physical library very often, but we receive so many benefits of having all of this digital library access, okay? And so so you can get like journal articles, which would normally cost like thousands of dollars a year for subscriptions and stuff, but they're all available for free. And one of the libraries that we have access to is Safari Books Online, okay? And I don't know if you guys are familiar with the O'Reilly series of programming books. Okay, so if you ever go to the bookstore, the UCLA bookstore, look at kind of their programming section, you're going to see a whole bunch of books that look kind of like this, okay? And they're published by O'Reilly, and they're normally like $50, $60, 40, 50, 60 bucks to purchase. But you can read all of them for free via Safari Books Online, okay? And all you have to do is be connected to the UCLA network. So if you're on campus, you can go to Safari Books Online, proquest.safaribooksonline.com, and check out, read any of those books, okay? If you're at home and you live off campus, you have to VPN in, right? You guys all know how have your VPN set up. If not, it's a good reason to set up. And you have access to this as long as you're a student at UCLA, which is pretty awesome. You know, the only thing is you have to read it in your browser, okay? So that's maybe not as nice as having a physical paper book, but it's still nice. Okay, so anyway, R for Data Science, written by Hadley Wickham, Garrett Grolman. Hadley's developed all of these packages for R, and he calls it the tidyverse, okay? And so the tidyverse is an opinionated collection of R packages designed for data science. All packages share an underlying design philosophy, grammar, and data structures. This is what he says about his own set of packages. And so, you know, what does it mean for, how is an R package opinionated, right? It's opinionated in the way that Hadley feels that the way we arrange our data should be a certain way, the way we interact with our data should be a certain way, okay? And I think this is common among like professionals and masters in their crafts, right? Like if you take cooking lessons from a master chef, okay, they probably have very strong opinions about what kind of knife you should use, how you should hold your knife, how you should use it, and stuff like that, right? And they're going to tell you this is the best way. And similarly, Hadley Wickham says he's the expert in R, and he says if we're going to interact with R, he thinks it should be done a certain way, and he's developed a bunch of packages to kind of deal with that. And I'm a believer in the tidyverse, and so in this course we're going to cover quite a few of these packages in the tidyverse. We've already talked about Reader, but later on we'll see ggplot2. Today we're going to talk about tidyr and Tibble and tidyr. On Monday we'll look at dplyr. Wednesday and Thursday we'll look at stringer, okay? The only ones we won't really have time for are purrr and forcats. but you can read those and stuff, okay? And you load them all using library tidyverse. Okay, library tidyverse will load all of these packages at once after you, of course, install .packages tidyverse. You know, like for today's lesson, you can just do library tidyr and call any one of these packages individually. But oftentimes you can just call in library tidyverse and it will load everything up, and it's quite a useful collection. Okay. All right. Throughout today's lesson and whenever you're dealing with the tidyverse, you're going to be dealing with what's called a tibble. Okay. A tibble is a data frame. Okay. A tibble is a data frame, except they've tweaked a few behaviors of the data frame. So there's, you know, when R was first created, computers had very limited memory. Okay. You know, you might have, you'd be lucky to get 1 megabyte of memory on your machine, and so storing string information in a table, character information, consumed a lot of memory, and so that's why they developed factors, where it turned the character information into integers, which take up less space. And the default behavior of data frames is to take character info and turn them all into factors. Which was useful back then, but today we're dealing a lot more in text data, and doing something like this is inconvenient. And so the tibble doesn't have that behavior, right? Strings as factors equals false is kind of the default behavior of tibble versus the data frame. And so anyway, this is what we're going to see. There's a few other things about the tibble. One of them is that tibbles print nicely onto the screen. Okay, so so here, the way you create a tibble is just like you create a data frame. Instead of doing data.frame and you say x equals this vector, y equals this vector, z equals this vector, you do tibble, and then you say x equals this vector, y equals this vector, and things like that. Okay, and so we're creating 5 columns. The first one has date information. Okay, the next one has the first one has date time info. The next one has date information. This has integers 1 through 1,000. This has doubles 1 through 1,000 random uniform numbers, and this one has character info. Okay, and when you print out a tibble, this is what it looks like. Okay, so one thing that's nice is that it only shows kind of the first 10 rows by default. Okay, and also each column on the heading, it includes what kind of variable it is. So here it says date time, date, integer, double. Okay, and then and it only prints the columns that will fit. Okay, so technically we could have fit column E on this thing, but I think the PDF specifications are such that, you know, it only fits a certain width here. Okay, and so it and then it says there's 990 more rows and 1 more variable E here. Okay, contrast this to a data frame. Okay, so I have a tibble. Let me just show you the diamonds data tibble. Okay, and this has 53,940 rows. It's got these columns. Okay, double, ordinal, and stuff like this. Okay, and it's got these things. Now, if you were dealing with a different window size, okay, and with the tibble you ask to print it out, you'll notice it still prints only the top 10 rows, and then the columns that don't fit, it just pushes aside and says, you know, there's 53,930 more rows and 3 more variables, x, y, and z, that is not included, just doesn't get printed here. Okay, contrast this to if I choose to print this as a data frame. Okay, what happens when you print a data frame? Okay, it kind of flushes out your entire thing, right? It tries to print out, so it prints out 100 rows. Okay, and and then it tries to get all the columns in there. So it gets all of these columns, and then the columns that didn't fit earlier, it's going to put down over here, okay? And then it says reached max, and it omitted this many rows here, okay? So contrast that, the as.dataframe where it goes like this, versus when it looks like a tibble, and the tibble we can see is just, it's a lot nicer to deal with in the console when you're working with stuff. So that's just some nice features. It's aware of how wide your console is, okay, all right, and prints accordingly, and it limits just to the first 10 rows. I guess it assumes 10 is the enough to kind of get a feel for the data, stuff like that, okay? Another thing is that tibbles, when you use a single square bracket to subset a tibble, it's always going to return a tibble, type tibble. So here, if I do diamonds and I say I want the, you know, 6th column, okay, it comes back as a tibble itself, okay? Whereas if I made this a data frame and I say I want the 6th column, then it turns it into a vector, okay? So using a single square bracket with a tibble always returns a tibble, okay? The exception is if you say drop equals true, you know, the drop option generally reduces things to a simpler form, okay? So you can say drop equals true, but otherwise it's going to keep it as a tibble. All right, and of course if you want to extract, so from the thing, you can always use the double square bracket, okay, and that pulls out, you know, the vector, right? Double square bracket or the $sign will pull out the vector. So those are some of the differences between tibbles and data frames. And pretty much when you're dealing with tidyr, everything it returns is going to be a tibble, okay? And pretty much most of the stuff that works for data frames will work for tibbles as well. But those are just some of the nice features here. All right, and so the idea is that when we're dealing with tidy data, we have these 3 cardinal rules, okay? Every variable gets its own column, every observation gets its own row, and every value has its own cell, okay? And that's kind of the guiding rules of tidy data, right? If every variable is not its own column, it's not going to be tidy, okay? And so how many observations you have is how many rows, how many variables you have is how many columns, okay? So that's kind of how we're expecting things, and when things are tidy, you have nice features, right? So this is tidy data, okay? Here we're looking at some information about storms. We've got the storm name, the wind speed, the air pressure, the date of the storm, things like this. And we can see each column is its own variable: storm name, wind speed, air pressure, and date, okay? Here's some other data that I would say is not tidy, okay? What are the, so this, I think, cases of some disease, okay? How many cases were there, I don't know, just in 2011 in France, right? Like, how many cases of whatever, something, okay? How many cases of something happened in France in 2011? 7,000. How many happened in 2012? 6,900. How many happened in 2013? 7,000. Okay, how many happened in the US in 2011? 15,000, and so on and so forth. Okay, this is all just made up data. What would you say are the variables that appear here? Now, we could argue that there's the variable 2011, the variable 2012, and the variable 2013. But what do you think would be a better variable than 2011, 2012, and 2013? What's that? Years, right? Okay, so we've got a variable for country, we got a variable for years, and then what would be the leftover, or not the leftover, but what's the other variable, that column name that we would need to keep track of? Just the counts of the cases themselves, right? Okay, and so if we ask how are these arranged, okay, the variables are country, year, and count, and the countries are in a column, but the year values are like column headings, and then the values are just kind of spread out around here, okay? So it's a little bit of a problem, right? over here, okay, we could, we look at this, we've got New York large 23, New York small 14, London large 22, London small 16, and this is, you know, talking about pollution amounts, okay? And so what are the variables that we have here? Right now, the variables say city, particle size, and amount, okay? But how many observations do you think we really have? So here we've got 6 rows, but I might argue that we actually only have 3 observations. We got an observation for New York, where we measured what? The number of large particles and the number of small particles, okay? And so here, our variables would be what? City, and we would have a column for, the number of large particles, and we'd have a column for the number of small particles, okay? And so the data here, city, amount of large particles, amount of small particles, if we look at the values for the amount of large particles, they're all mixed in the same column as the amount of small particles, okay? And can you imagine trying to do an operation, some kind of calculation here, okay? Here, let me just show you. When you have data in, okay, this is how we read in the data. The data is all available on GitHub, and so here are the different URLs, and you can copy them in. When you have data in tidy form, like we have here, you can do vectorized operations. So I can just do, you know, the air pressure. I don't know if this is even a useful calculation, but I can just do air pressure divided by wind speed, right? Storms $ pressure divided by storms $ wind, and it does vectorized operations. It's going to do 1007 divided by 110, it gives me 9.15. 1009 divided by 45 gives me 22.4, and it does every row. It does a vectorized operation, and this is very useful for us. Okay. Can you imagine trying to do a vectorized operation for, or not, you can't do a vectorized operation. We're trying to do some kind of calculation here where we said, you know, let's compare the difference between large and small particles in New York, large and small particles in London, large and small particles in Beijing. Like, how would you go about doing something like that? It'd be a bit of a nightmare, right? You'd have to figure out some way to subset all the even rows, or subset the rows that correspond to large, subset the rows that correspond to small. It's going to be a mess, okay? And so this is one of the many reasons why we prefer working in tidy data, is that you can do these vectorized calculations and operations here, okay? So what we're going to do is we're going to take a look at how we can convert tables that look like this or tables that look like this into tidy form, okay? So first of all, we're going to take a look at the cases data, okay? So here's our cases data. Okay, we've got a row France, Germany, US, and we've got data for the columns 2011, 2012, and 2013, okay? So here's a question. If we make this tidy, okay? If we make this tidy so that the resulting variables are the country, the year, and the count, what will be the resulting dimensions? All right, so think about how this table will look if we decide to make this tidy. All right, and then once you think you know what it should look like, just turn to your neighbor to confirm that you guys are on the same page here. So the dimensions being how many rows will you have, how many columns will you have. I'm expecting a little bit more chatting with the neighbor. Okay, so we want to change what we see here into tidy data, so we have one column for country, one column for year, and one column for count. Okay, what do you guys think? What will the resulting data frame nor tibble look like? Dimensions will be... Anybody? Do we understand the question? No? Maybe? Okay, here, I'll just show you the answer, and maybe this will help, okay? So we want to turn this, right? We want to make this into this. We're going to get resulting will be a 9x3 tibble, okay? So this is what we get, okay? So this number 7,000, right? France 2011 7,000 ends up in this row where it says France 2011 7,000, okay? And then this Germany 2011 5,800 ends up in this row. Germany 2011 5,800, and then US 2011 15,000. The next value right here, this one, is going to be in the row France 2012 6,900. Here is Germany 2012 6,000. This value ends up here. This value US 14,000 in 2012 ends up right here. Okay, do we understand how we go from here to here? Okay, does that make sense that we go from a 3x4 to a 9x3? Is that okay? All right, and so how did we fill in these values in this column year? What did we do? With the values 2011, 2012, 2013, where do these values come from? They came from the column titles, right? So what we did is we said we're going to take these columns, 2011, 2012, 2013, and we're going to put them into one column, okay? And then this column N got populated by what? All the values that show up there, okay? All right, and so the way we would do this, okay? So the command we use is called pivot longer, okay? Because we've got, this is our original data, and we want to kind of pivot our data in such a way that the result is going to be longer than how it started, okay? So we're going to pivot longer, and we see we get, okay, I wasn't sure if that was something we should be worried about, but okay. So we do pivot longer, and we've got the columns. What we're going to do is we're going to kind of take the columns 2011, 2012, and 2013, and I can specify that with the colon, okay? I can say 2011 through 2013, okay? 2011 through 2013, you can use colon notation. And we're going to take those columns and basically gather them, okay? Put them together. We're going to pivot them longer, okay? And the names of these columns will go into this the column called year, and then the values in those columns will go into the column, here I call them cases, okay? It looks like just it arranged them a little bit differently, but it's the same idea, okay? 9x13 here did France, 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 Germany, 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 US, 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 okay? 2011, 2012, 2013. All right, is that okay? What this does? All right, and so just kind of the specifications for all of this, the arguments that you need to specify are the data is the what data frame you're dealing with. Columns are the names of the columns you're dealing with, okay? You can use colon notation. So if you have the names, if the column names are like for months, January, February, March, April, May, June, so on and so forth, you can say January, December, and it's going to gather, kind of take all 12 of those months, okay? You can also give it a vector of character names, of the column names, or you can give it a vector of index positions. You can say, I want the 4th column, 7th column, 8th, and 9th columns, or something like that. So you can give it a vector of column positions as well, okay? The names too and the values too, these are just character strings, okay? They can be whatever you want it to be, all right? So for example, these are terrible names to use, but there's nothing wrong by saying the name is when it happened, and the values to name will be how many, okay? Generally, we like single word names that are a little bit descriptive, but there's nothing inherent about using the name year or using the name n, or using the name cases, or anything like that. It's just an arbitrary string that is going to be the column heading here. Okay, and so it forms this. Is that all right? Okay, let's just double check our understanding here. So here's, again, our data table, original data. What if the columns that I pivot, I only pivot columns 2012 and 2013? Okay, so I don't pivot column 2011. So the command I'm going to use is going to be columns to pivot 2012 through 2013. What's going to happen here? What will the resulting data frame, how many rows will I have, and how many columns will I end up having? Okay, so what do you guys think? How many rows will I end up having after I pivot longer? 6 rows, okay. And how many columns will I end up having? Here's the follow-up question then, okay? If I'm only going to have 3 resulting columns, what are the columns? What are those 3 columns then? Country, year, and count. Why did you pick country and not 2011? Okay, so the answer is that because we didn't, like, R doesn't understand this, right? It has no semantic understanding, so it doesn't know that country is more important than the column 2011. So it's going to keep both of them, all right? So the resulting thing is going to be 6 by 4, right? Like you understand and say, okay, well, it makes sense to keep country but not 2011, but that's not what we're doing. It's going to keep everything that you didn't say to pivot, okay? So in this case, anything we didn't say pivot will get duplicated, all right? So in our case, country in 2011 gets duplicated, so each of these things, France and 7,000 shows up twice, Germany and 5,800, and US and 15,000 show up twice, and the 2 columns we did pivot, I think, has the behavior that we expected, okay? 2012 and 2013 get gathered together, and then the cases, those get gathered together as well. Does this make sense? Why the result is 6 by 4. Okay, so I think you guys got the 6 part, and then the 4 part comes from the fact that anything that we didn't pivot will just get duplicated. Those remain as part of the original data, right? Okay, this is a bad idea, okay? But what if I decide to include country in the columns to pivot? So I'm going to pivot country, the columns country through 2013. What if I decide to include this in the columns to pivot? What will the result be? Okay, so how many rows will I end up having? How many unique values appear? Or not unique, but how many values appear? 12, so I'm going to have 12 rows. How many columns will I end up having? 2. What are my column names? It's going to be name and value as listed here. The name's 2 and the value, right? Okay, so actually, when we try that, actually R gives an error, okay? R has a little bit, the tidyr package actually has a little bit of sensibility, right? It says, okay, I'm going to try to combine these things. These ones are numbers, these ones are type double, but these ones are character. So I don't think we're supposed to do this, right? So it's actually going to error out. It's going to say no common type for country, which is character, and then the first column that it's trying to pivot with, 2011, which is type double. So it actually gives you an error, okay? So that's a nice thing, okay? Because it might prevent you from doing something silly, okay? But let's say I'm going to force it through. So I'm going to convert the entire data frame to character type, Okay, so we're not going to run to this type and mismatch. So I do that right here. I do an lapply and I do an as character, and now I say pivot longer. Okay, so because everything is character type, I don't run into the type error, and then this is the result I get. I get a 12 by 2. Okay, it indeed pivoted all the columns together. Okay, including the country one. Okay, and so we get country France, this, country Germany, country US, and also all of the other things. I'm gonna get 12 by 2. But these we've lost a lot of meaning, right? Now we have a bunch of 2011s and a bunch of 2012s. We got, rows that are difficult to differentiate from each other. So it's not a good idea, okay? And I only do this to kind of illustrate what happens when you run these this pivot longer thing into situations that might not make as much sense. Okay, so both of these are kind of not wise decisions, but the package just behaves in a very predictable way. All right, is that all right for pivot longer? Okay, let's do the opposite here. Okay, so here we've got one column amount where all the values are stored in this one column amount. Okay, and so what if I wanted, what I want to do is I want to kind of take those values in amount and put some in the column for large particle amount and some in the small particle amount column. Okay, so the other one was called so what will the resulting dimension be? The resulting data set. What dimension will we have here? So the variables in the resulting data set will be city, large particle amount, and small particle amount. So this will have dimensions what? I think you guys got it. 3 by 3, right? So this is what it looks like. Okay, so we're going to go from here and we're going to go here, right? So New York 23 goes into the large, New York 14 goes into the small, London large 22, London small 16, Beijing large 121, Beijing small 56. Okay, so this is what we end up getting, a 3 by 3. So the other function was called pivot longer. This function to do this is called pivot wider. Okay, so pivot wider. It used to be called spread, but we have pivot longer and pivot wider. Okay, and so we're going to pivot wider only takes 3 arguments. We're going to say take the tibble name, the name of the data frame, pollution. The names come from the size column. So this is the size column, and the names for the new columns, okay, come from that size column. So we're going to have a column for large and a column for small. Okay, and then the values that we populate it with come from the amount column. So it says names from size, values from amount, and that's how it works. Okay, so this is pivot wider. We have pollution, names from size, values from amount, and these are the names of the columns that we're going to pivot from. Okay. So pivot wider is sensitive to spelling differences. Okay, so here I took the pollution table and I duplicated it to pollution 2, and I purposely messed things up. Okay, so I changed that first New York to NYC. So New York is now New York City, NYC. Okay, and so this is what our data looks like. All right, let's say I run the same command that I did before, okay, except now with pollution 2 where I've changed this, okay, pollution wider. We're going to get column names from the size column, values from the amount column, okay. What will the resulting data frame look like? How many rows will I have? How many columns will I have? How many rows am I going to have? 4, right? I'm going to have 4 because if we look at this column that's not being pivoted, how many unique values are there? We've got 4 of them. We've got an NYC, a New York, a London, and a Beijing. Okay, so we have 4 unique values here. And so when we pivot them, this is what it looks like. I get 4 rows and 3 columns, a column for large and a column for small, okay? And basically we have a NYC large value is 23, and we have nothing for the small, so that gets an NA. And then the New York has a value 14 small, but then there's nothing for large, and so that gets an NA. The London and Beijing get pivoted the way we would expect them. All right, is that all right? As far as why we're getting 4, it's because over here we've got 4 unique values as far as the columns that aren't being pivoted. Okay, let's just mess with this a little bit again. So again, I duplicate the original pollution data, and here I change the spelling of large to all caps large. Okay, so the size column has all caps large, small, lowercase large, and so on and so forth. I'm going to do the same command before, pivot wider. Names from size, values from amount. So what will the result look like here? So how many rows will I have? 3, New York, London, Beijing. How many columns will I have? 4. I'm going to have city, and then numbers for all caps large, numbers for small and lowercase large. So this is what I end up getting. Okay. So does that make sense as far as what's going on? And again, what it's doing is it's the thing, it has no semantic understanding of words, right? It's just looking for unique values. And so each unique value is going to get its own column heading, and it's going to try to match up the values accordingly. It's a very powerful tool. It's very useful. But again, it's sensitive to these kinds of small mistakes, right? So if you have something spelled one way in this thing and something spelled another way, it's going to throw stuff off like this. So pivot longer and pivot wider are basically inverse operations, right? So just to kind of reiterate this, so here is the original pollution thing, okay? And I had to make it small so everything fits. And if I do pivot wider, okay, I get this 3 by 3. So that's pivot wider. This is exactly what we did before. Names from size, values from amount. This is the result. And I've stored this as W, okay? And with W, if I take this and I say pivot longer, right? So I take these things and I say I want to gather or put the large and small values into one column. I do pivot longer, and I say the columns that I'm doing are large and small, the names to size and the values to amount, and we get back basically the original data frame that I have up here. Okay, so pivot wide and pivot longer basically undo each other, all right? And similarly, if I do the same thing with cases, first we did pivot longer and we got this. And if you wanted to undo this one I call L. And if you wanted to kind of undo this or go the other way, you can do take this L, which is pivot longer, and then you just pivot it back wider, and you get back the original thing, right? So these are inverse operations, and so depending on the data that you've gathered or the data you've collected, you might want to pivot them longer, you might want to pivot them wider, okay? And again, you know, a lot of it comes down to how do you want to think about kind of your vectorized operations, right? So if you want to, when you have tidy data, you can do vectorized operations between the columns and do all sorts of calculations. It's very useful and powerful. So, all right, are there questions on this? We're all good? Okay, all right. Well, that's today's lecture then. We'll end here for now. Get out a couple minutes early, and we'll see you guys on Monday. Have a good weekend.